Hey everyone, and welcome. Today we are going to tackle a fundamental rule of the universe, and we're going to start with a really simple, almost magical question. How in the world does a little bit of fire lift a giant hot air balloon? Let's dive in. I mean, really think about it. Just seems wild, doesn't it? You've got this burner blasting fire into this huge bag, and then somehow the whole thing, the basket, the people, all of it just floats up into the sky. How does that actually work? Well, that's the puzzle we're going to solve together today. So here's our game plan. We'll start with our balloon, then we'll get into the energy accounting rule that makes it all possible. After that, we'll look at 4 specific thermodynamics situations, pop them all into a super handy cheat sheet, and then we'll talk about why this one law is so critical to, well, pretty much everything.
All right, let's get right to it. Our hot air balloon. It is the perfect real-world example for what we're talking about today, because you can literally see the physics happening right in front of you.
Okay, let's break this down. First, that burner adds heat. Simple enough. That energy gets absorbed by the air molecules inside, and they start zipping around like crazy. That right there is an increase in the air's internal energy. Now, all those energized, bouncing molecules need more room, so the air expands and pushes against the inside of the balloon. That physical push, that expansion, that's what we call work. So you see, heat goes in, energy goes up, work comes out. So that one example just gave us our 3 main characters in this story: heat, internal energy, and work. Let's get to know them a little better and learn the language physicists use to talk about them. This is the foundation for everything else, so this is important stuff.
First things first, we've got something called state variables. You can just think of these as the stats of a system. You know, like in a video game? At any moment, you can look at its pressure, its volume, and its temperature. And those 3 numbers tell you exactly the condition or the state that it's in. These are our fundamental measurements.
Next up is internal energy, which we usually write down as a capital U. This is basically all the energy that's just humming away inside the system. It's the chaotic, kinetic energy of all those molecules bouncing around. So when we heat up the air in the balloon, what we're really doing is cranking up this internal energy.
And that brings us to heat, or Q. Now this is a super important point. Heat is not a thing. You can't hold heat. Heat is the process of moving energy from a hotter place to a colder place. So the flame isn't giving the air heat, it's transferring energy to the air as heat. It's a small difference in wording, but a huge difference in concept.
And finally, there's work, which we call W. This is the payoff. This is the useful thing we get out of all this energy. When the gas inside the balloon expands, it physically pushes the fabric outwards, making the whole thing inflate. That push over a distance, that change in volume, that is work. It's energy being put to use to do something tangible. So, we've got our 3 players: internal energy, U, heat, Q, and work, W. And the first law of thermodynamics is this beautifully simple yet incredibly powerful equation that ties them all together. You can think of it as the universe's unbreakable rule for keeping track of energy.
So let's break it down. That little triangle, delta, just means change in. So the change in a system's internal energy, delta U, is equal to the heat you add to it, Q, minus the work the system does, W. Basically, it's an energy budget. Any energy you put in has to go somewhere. It either gets stored inside as internal energy, or it gets spent to do work. None of it just vanishes. You can't create it, you can't destroy it. That's the law.
Okay, now that we have the master rule, let's see how it plays out in 4 very specific situations. Think of these like 4 different strategies a system can use to manage its energy.
So on one side, you have an isochoric process. Iso means same, choric means volume, so constant volume. Just imagine heating up gas in a sealed metal box. It can't expand, right? So no work can be done. Every bit of heat you pump in just goes into raising that internal energy. But on the other side, you have an isobaric process, constant pressure. And yep, you guessed it, that's our hot air balloon. It's open at the bottom, so it's always at atmospheric pressure. In this case, the heat you add does 2 things at once. It raises the internal energy, and it does work by making the balloon expand.
Then there are these 2. An isothermal process means constant temperature. Here, any heat you add gets instantly and perfectly turned into work. The internal energy doesn't change at all. It's like a perfect conversion machine. And finally, you have an adiabatic process. This is when a system is perfectly insulated. Think of a really good thermos. No heat gets in or out. So if the system does any work, like a gas expanding, it has to pay for that work by using its own internal energy, which means it gets colder.
Whoa! Okay, I know that was a lot of new ISO words, so let's put it all together in one place to make it super clear. This is our cheat sheet.
Look at how our master equation, delta U equals Q minus W, gets simpler in each case. For isochoric, work is 0, so the change in energy is just equal to the heat you add. For isothermal, the internal energy change is 0, so heat in equals work out. For adiabatic, heat is 0, so any work done comes straight out of the internal energy. And then there's our isobaric balloon, the one where all three parts of the equation are doing something. This table, right here, is really the key takeaway from all of this.
So we've gone from a balloon to an equation to 4 different processes. But why does this matter so much? Let's zoom back out and look at the big picture. It all really stems from the incredible work of people like James Prescott Joule. He was the one who proved, beyond a shadow of a doubt, that heat and work aren't separate things. They're just 2 sides of the same coin, energy. And you can turn one into the other. That idea completely changed the world.
And I mean, this principle is everything. It's what makes a car engine go, turning the heat of tiny explosions into the work that moves your car. It's how your refrigerator works. We're using work to move heat from inside to outside. Power plants, jet engines, air conditioners, they're all just really clever applications of the first law of thermodynamics.
And that leaves us with one final, very cool question to think about. If the first law says energy is always conserved, you get out what you put in, then why can't we build a perfect engine that wastes 0 energy? Why is there always some waste heat? Well, that, my friends, is a story for another day, and it's a puzzle that's solved by the second law of thermodynamics. Thanks for tuning in.